You've learned the PKCS number 11 concepts. Now we'll plug them into real code. In this module, we'll connect Java, C, and C++, .NET, Python, and other stacks to Luna HSMs, so your applications use hardware-backed keys for everyday cryptographic operations. You now have the full picture from hardware concepts through PKCS number 11, what a Luna HSM is, how clients connect, how keys live and move, and how applications see objects and mechanisms. Now we'll turn that foundation into concrete, language-specific application code you can actually implement. When you integrate with a Luna HSM, you're really choosing how close your code gets to PKCS number 11. At one extreme, C or C++ talk directly to the PKCS number 11 API. That's fast, powerful, and very detailed. Java typically uses provider frameworks like JCA or JCE, trading some control for portability. Languages like Python, .NET, or Go often rely on wrappers or even external helper processes, which simplify development and improve isolation. In Java, integration with a Luna HSM is all about layering. Your code uses familiar JCA and JCE classes like KeyStore, Signature, and Cipher. Those calls are routed into a security provider, such as SunPKCS11 or a Luna-specific provider, which speaks PKCS number 11 to the HSM. That provider is the bridge. It exposes HSM-backed keys through a PKCS number 11 KeyStore, and provider order controls which implementation Java actually uses. To let Java talk to the Luna HSM, you first configure a PKCS number 11 provider. The configuration gives it a friendly name, points to the Luna PKCS number 11 library, and tells it which slot or token to use. Avoid baking absolute library paths into code. Use environment variables or deployment configs instead. In production, prefer selecting by token label, since slot numbers can change between machines or after hardware changes. In this setup, the Java KeyStore is really just a directory of aliases. When you call KeyStore.getInstance PKCS11 provider, each alias maps to a key object inside the Luna partition, not to raw key bytes in the JVM. Your code still calls getKey, signs, or decrypts as usual, but the HSM performs the operation. Private key material never leaves the hardware, so Java only ever handles references, not exportable secrets. For signing, the Java Signature API is just a front end. The actual private key work happens inside the HSM. You load the PKCS11 provider, open the HSM-backed KeyStore using a pin, and obtain a private key handle, not the raw key bytes. Then you create a signature with an HSM-supported algorithm, initialize it with that key, stream in your data, and call sign. Make sure you handle provider and authentication errors explicitly, so failures are clear and secure. Java decryption with a Luna HSM depends on choosing mechanisms the device actually supports. Your Cipher getInstance string must match the provider and the key's attributes, including padding. RSA here is mainly for unwrapping a data encryption key, not for streaming large payloads. Bulk data should use symmetric ciphers in your application. If decryption fails, suspect padding, key usage flags like CKA decrypt, or a mismatched mechanism choice. When you program directly in C or C++, think of PKCS number 11 as a strict lifecycle. You load the vendor library, initialize it, discover a slot, open a session, and log in before touching keys. Session and object handles are just runtime tokens. Never cache or serialize them. Every API returns a CKRV, so treat failures like exceptions and bail out early. Finally, always log out, close sessions, and call finalize to avoid leaks or stuck tokens. You can also think of PKCS number 11 integration, like managing file descriptors in C. Every session you open must be closed on all paths, including error and early return paths. Treat CK object handles as short-lived. When you reconnect or fail over, rediscover objects instead of trusting old handles. For concurrency, either give each thread its own session or guard shared ones with locks. And always translate CKRV into clear, secure log messages, never including pins or secrets. In C and C++, PKCS number 11 crypto is all about following the correct sequence. First, you log in and search for the right key object, usually by label. Then you pick the mechanism that matches both your algorithm and key type. For signing or encryption, you always call the init function, then the single pass or multi-part operation. Buffer sizing is typically two-step. Call once with a null buffer to get the size, allocate, then call again, and always check return codes. With .NET, it helps to think in terms of three patterns. PKCS11 wrappers give you the most direct control. You decide sessions, mechanisms, and key usage, but you manage native libraries and error handling yourself. Windows providers plug into CNG or KSP, so your code uses familiar .NET and certificate store APIs, trading some control for easier integration. Internal crypto services put the HSM behind an API, centralizing policies and credentials, but adding network hops and operational overhead. Now picture a Python script that signs PDF reports overnight. It loads a PKCS11 module, opens a session to the HSM, authenticates, finds the report signing key, signs the document hash, and writes the signature back to storage. This is ideal for automation and CI pipelines, as long as you manage library paths carefully, handle concurrency, and surface rich PKCS11 error details in your exceptions. Choosing a language strategy is all about trade-offs. Java providers sit in the middle. Good integration with existing JCA, JCE code, moderate control, and familiar operations. Direct C or C++ PKCS11 gives you the most control and performance, but demands deep expertise and heavier operations. .NET and Python wrappers emphasize developer productivity and ecosystem fit. Crypto services centralize HSM access, improving consistency and governance at the cost of an extra network hop. You've now seen how Java, C, and C++, .NET, and Python each reach Luna in their own way. Next, we'll zoom out from code details to integration patterns and start designing secure, scalable, production-ready architectures.